Hello everyone, I am Mallar, the Assistant Professor of Mechanical Engineering of Mallar Institute of Technology, trying to explain the steady flow energy equation and its application. As introduction, it can be said that from the first law of thermodynamics, we know that the total energy entering the system is equal to total energy leaving the system, and this law is applicable for the steady flow system also. The system is considered as a control volume system, that is otherwise the closed system, and there is two outlet, one is inlet and other is outlet, and there the energy with mass entering the system and then exit from the system. During this, something stored in the system. The steady flow energy equation followed this, and the summation of energy contained with the internal energy, the kinetic energy and the potential energy. There is some consideration considered in the steady flow, and those are the mass flow rate of flow into and out of the control volume are equal and constant with respect time. Number 2, the state of fluid at any given location does not vary with time, that is, all terms involving ddt are 0. Number 3, the rate of heat transfer and work transfer are constant in this process. Next, the flow process. The steady flow energy equation of unit flow is given by dimensional constants to be checked when used. It is shown as like that: U1 plus P1 V1 plus V1 square by 2 plus GZ1 plus Q to the inlet of the system, and the outlet of the system, that is U2 plus P2 V2 plus V2 square by 2 plus GZ2 and WS. Here the WS is the shaft workout. And then what is U1? U1 is the internal energy to inlet, and P1 V1 the control volume and pressure to inlet, and V1 square by 2 the velocity of fluid to inlet, and GZ1 the potential energy to the inlet, and the Q is the heat. The other outlet, that is U2 is the internal energy to outlet, and P2 V2 the control volume and pressure, V1 square by 2 the velocity of fluid to the outlet, and GZ2 the potential energy to the outlet, and W is also the work done by the shaft. And now what happened if we replacing the internal energy with enthalpy H? Then what happens? Then it is looks like that: H1 plus V1 square by 2 plus GZ1 plus Q. This is to inlet, and the outlet is H2 plus V2 square by 2 plus GZ2 and shaft workout. In the otherwise, it is also be said in other term, the energy going into the control volume minus energy going out of the control volume, then energy stored in the control volume. This statement is the other view of this steady flow energy equation. The summation of the energy is internal energy plus kinetic energy and potential energy to inlet, and the same thing to the outlet, and it is expressed by the below equation, and that is M with potential energy, internal energy and kinetic energy to inlet, and same thing to the outlet. If we subtract inlet to outlet, then what happened? Energy going to in minus energy going to out is equal to 0. And this statement, if expressed by equation, that is looks like the below form. And then if with the internal energy replaced by enthalpy, that is look like H1 plus V1 square by 2 plus GZ1, and in the outlet, that is H2 plus V2 square by 2 plus GZ2. After this, the steady flow energy equation, it is required to know the applications of steady flow energy. The application of the steady flow energy equation can be used to study the performance of many engineering devices that undergo the thermodynamic process. At these devices closely satisfy the conditions of steady flow processes. For example, the engineering devices like broiler, turbine, condenser or heat exchanger, feed water pump, cooling tower, and stack of steam power plant run non-stop for many months before these are shut for maintenance. Therefore, these engineering devices must run under steady state conditions and can be analyzed as steady flow devices by applying steady flow energy equation. And that the picture shows a power plant with consists with thermodynamical devices as like a cooling tower, broiler, turbine, condenser, water pump. Those all things are played with the steady flow energy equation. And now individually I discuss the 6 thermodynamical devices in this video, and those are at first the nozzle, and then the broiler, and then condenser, and then evaporator, then turbine, and rotary compressor. Nozzle. This is a diagram of a nozzle where showing a inlet part and outlet part, and the nozzle covered with the insulator. So the nozzle is contributes to increase kinetic energy of the flowing substance at the cost of pressure drop. This section deals with the nozzles only from the point of view of the application of the steady flow energy equation. We have H1 V1 square by 2 plus GZ1 plus Q2 inlet and H2 V2 square by 2 plus GZ2 plus WS to the outlet. The shaft work is obviously 0, so WS is 0. The nozzle is thermally insulated and characteristic by the high rate of flow of fluids. Thus, heat transfer is also negligible. That's why Q also be 0. The change in elevation between the entry and exit point also be negligible. That's why Z1 minus Z2 be also be 0. Then the remaining part is H1 plus V1 square by 2 to inlet and H2 plus V2 square by 2 to outlet. So simplify this equation. The nozzle equation is at last V1 square by 2 minus V1 square by 2 is equal to 2 H1 minus H2. That is the nozzle equation from steady flow energy equation. Now the broiler. Broiler is very important part in power plant, which is considered as a source in the power plant. So what happened? In the broiler is characterized by the following features. Velocity change is not applicable or may be neglected. That's why the kinetic energy is 0 in this case. Elevation change between inlet and outlet point also be negligible. That's why it is 0 and there is no shaft work. And then the WS also be 0. Then what happened to the remaining part? The remaining part is Q is equal to U2 minus U1 plus P2 P2 minus P1 P1, which is replaced by enthalpy. It is look like Q is equal to H2 minus H1. This is the equation of the broiler. After broiler, the condenser. This is also a very important part in a power plant. So what happens in a condenser? Primary function of a condenser is the transfer of heat out from the steady flow system. In this case, no shaft work, so W is equal to 0. No change in kinetic energy, that's why kinetic energy part also be 0. No change in potential energy, so this part also be 0. One steady flow stream is that of vapor which loses heat at constant pressure at it passes over the tubes through which another steady flow stream of coolant is passing and receiving heat at constant pressure. That's why the remaining part is mh1 minus mh2 is equal to q. Simplify this equation, this looks like q is equal to m under bracket h1 minus h2, which is the steady flow equation for condenser, and then evaporator. This is also a very important part. So what happens for evaporator? The process occurring in evaporator is the reverse of what happens in a condenser. In evaporator, liquid enters, receives heat at constant pressure and leaves as vapor in this case. That's why there is no shaft work, so WS is 0. Kinetic energy change is negligible, so that part also be 0. Then the potential energy change is negligible, so that is also be neglected. So reducing all those things, we have q is equal to m of under bracket h2 minus h1, that is just opposite of the condenser, and it is the equation of evaporator by steady flow energy. And then the turbine. This is a very important part which can convert the steam into electricity. So what happened in turbine? That is also h1 minus h, and for rotary compressor that is same. Okay, thank you very much for watching this video. Please like, comment and share.